area under the normal curve. So where's my pen stuff? There it is. Got that. Okay, so I'm going to draw a little normal curve up here. And remember, we always put mu there. That's a little thick. Let's try that one. And as long as we were able to look for areas that were exactly 1, 2, or 3, or by factors of the standard deviation, we could use the empirical rule. But that's just asking too much to say that all the probabilities that I want are going to have to be factors of the standard deviation away from the mean. So if we just want a generic, what is the probability of coming in at less than or equal to x? Then we're talking about the area under the curve here. And we don't have a real easy way to calculate that because we can't draw rectangles because we've got this smooth curve. So what are we going to do? And that's what today's class is going to discuss, how we're going to deal with that. And it turns out that we don't have to maintain data for every possible type of normal curve. Like you might have one normal curve that has a mean of say 100, and some other normal curve has an unusual mean, something like 36.5. So if you notice, this might be one standard deviation away. Let's say a standard deviation is 10, and that's 90, and this is 110. And here a standard deviation maybe is 2, so this would be 34.5, and this would be 38.5. So if I asked here, what's the probability that x comes in less than 90? It's the same as the probability for this distribution that x comes in less than 34.5, because both of those are on a normal curve, and both are one standard deviation away from the mean, so they incorporate that portion over there. But the values are entirely different, yet they have the same outcome. So what we do is we can take these and we can kind of squeeze them into a singular definition for a random variable, and we're going to reserve the capital letter Z for a standard normal. So we call it Z. And it's a simple calculation. I just need to take whatever value I'm interested in from the underlying normal distribution, subtract from that particular value the mean for the standard distribution, for the normal distribution, and divide by the normal distribution's standard deviation. And that's going to standardize it and make a new normal distribution whose mean is 0 and whose standard deviation is 1. So I'm always, so this is Z. So now if we're talking about this same region, we would call that the probability that Z is less than -1, because all three of these cases were one standard deviation away. So what we do is we compress whatever we got into this form by using this formula, and then we look at z, a standard normal variable, instead. Okay, so I've done a lot of talking about this in generic terms, so let's look at a specific situation. So we have a pediatrician that obtains heights of 3-year-old female patients, and we can consider the normal distribution, so that's just telling us it's got that bell curve. The empirical rule applies. But its mean is 38.72 inches, and the standard deviation is 3.17 inches. So we're going to use the normal model and determine the proportion of the 3-year-old females that have a height less than 35 inches. Okay, so I'm going to create a new slide here. And I'm going to go ahead and copy this problem so we got some new space. All right. Okay, well, let's draw a picture of this because that's always a good way to start. It's a normal distribution, so we're talking this little bell curve. They've told us my drawings will not be perfect. Try and use your imagination to clean them up a little bit. The mean is 38.72. And the standard deviation is 3.17 inches. So if I'm one standard deviation, remember we're looking about where that inflection point is. So just a simple calculation of 38.72 minus 3.17. So to be one standard deviation away, it's going to be 35.55. And I would encourage you guys to do this with me on your calculators and correct me if necessary. Okay, so all I've done is taken the one standard deviation. So here's one standard deviation to the left of the mean, and if I add the standard deviation of 3.17 to 38.72, then I get 41.89 as the label for one standard deviation above the mean. And what we're interested in is we want to find the proportion of 3-year-old that have a height less than 35. Remember, the proportion of the population is the same as the probability that if you randomly selected a 3-year-old female, they would have a height of less than 35. So we're answering the same question either way. So what we're asked for is the probability X is less than, and remember with a continuous distribution, that's the same as less than or equal to. So it's up to you if you like to use that. So 35. So what I'm going to do is I'm going to go locate about where 35 looks like it would be. Well, this is 35.55, so it's going to be just a little bit to the left. So I'm going to kind of take liberties here with my red pen. And what we're interested in is the area beneath the curve. Less than means to the left of. If they just said greater than, we'd have to figure out how to calculate the area to the right of the curve. We'll worry about that later. Okay, so what we need to do is go back to our z. We're going to convert to standard normal. We convert to a z value, that way we can use standard normal. Okay. So z is equal to the x value in question minus the mean of the underlying distribution, that was 38.72, divided by the standard deviation, which is 3.17. Okay, so maybe one of you can get ahead of me here and let me know what z-value we're interested in. We know it should be a negative number because if this is going to be a 0 in standard normal, then something to the left of it's going to be negative. And that's what will happen here because 38 is bigger than 35. All right, so anybody to the nearest 2 decimal places? Remember, you learn by doing, so all right, well, if you plug that into your calculator, you should end up getting negative 1.17 to the nearest hundredth. So now what we've got is an equivalent probability that z is less than negative 1.17. Okay, so if I draw this was x. Let's draw it for z. So in terms of a standardized normal, it's the same region, it's just in terms of a standard deviation of 1 and a mean of 0. Okay, so why is that good? Well, I'm going to refer you now to, if you go to your course content, and under week 10, I've got this standard normal distribution table. This is available to you in your text, and I've also got it here. So I'm going to click on that, and we're going to look at that. And the way we read that is it's a normal distribution, which is what we see in the picture of here. And all of these values inside the table are the areas of different z values. So it gets as comprehensive as you're probably ever going to need, giving you different areas by increments of the z-score. So what we have to do, and then this represents, like for instance, for a z-score of negative 2 point, so I get the left of the decimal in the column, and then I get the first decimal point in the column as well, but then I have to go add to that the second decimal point along these columns and find the area that corresponds. So let's say I'm interested in, I don't know if my pen's going to work here. No. I'm interested in z of negative 2.2. Well, I find negative 2, and negative 2.2 is right here. And then I don't want to add anything to the second decimal place. So for negative 2.2, the area under the curve to the left of negative 2.2 is 0.0139. Okay, let me enlarge this a little bit. Let's say I was interested in the area to the left of 0.17. Okay, so I come down and I find 0.1 here, and then I have to go find 0.7 to tack that on and get 0.17. So the cross intersection of 0.1 and 0.07 has an area under the curve to the left of 0.5675. Okay, so that's how we read this table. So let's go back to our problem here, and we're interested in a z-score less than or equal to negative 1.17. So if I go to the table, really wish I could mark on that. Let me try this.
Thank you.
All right, from our last slide, we were looking for probability that z is less than, or we could say less than or equal to negative 1.17. Okay, so I got to get the negative 1.1. So we're talking about this row. And I got to tack on an 0.7 to get a negative 1.17. So we're talking about this column.
0.1210.
Good. We home in on the intersection, and that's 0.1210. So we now know that the probability that x is less than or equal to 35. Remember, that was our original question. That's equivalent to a z-score of negative 1.17. So it's going to have the same area under the curve to the left of that value because those correspond. So back to being in terms of our underlying normal variable, which has less than 35, it has the same. Okay, so that's our tool there. And the table, okay, so what we end up wanting to do, I'm going to move this slide up one here. We're going to do it like this. Okay, so let's start with a fresh question. Okay, feel free to read ahead and get started if you're comfortable. Pediatrician obtains the heights of a 3-year-old female patients. The heights are approximately normally distributed with a mean of 38.72 and standard deviation of 3.1. Same information as our last question, but now we're going to be asked what's the probability that a randomly selected 3-year-old girl is between 35 and 40 inches tall. So we've got a different scenario altogether. We're interested in between 35 and 40. So we've already got a z-score for 35. We said that was negative 1.17. We need a z-score for 40. So our z-score for 40 or z-value is probably a better way to say it. I have to take 40 minus 38.72 divided by 3.17. Okay, so we get 0.4038 for our z-score, but if you think about it, you're only needing 2 decimal places to read the table, so I'm going to round that to 0.40. Okay, so let's rewrite this in terms of standard Z. So what we're interested in is a probability that we go -1.17 less than, or you can use less than or equal to if you want, Z less than 0.40. Okay, in terms of the graph, oh man, I hate it when it slides on me. The slides are sliding. Now you know why. Okay, and then the -1.17 is probably somewhere about right here. And then the 0.40, it's not lining up. I don't know if you can see that, but that's really wicked. Okay, and then what I'm interested in is that area there. So we have to, in order to do this, we need to take, so what I'm interested, that's just not gonna work. Let me go to a new slide, see if it happens. That's better. So any ideas how we can calculate that area? I've got a problem here. I need to, if it were only less than, if I were only interested in less than 0.4, then I could calculate all the area to the left of this and shade the rest of this. Problem is, I don't want that portion to the left of -1.17, so what am I going to do? Anybody have any ideas or thoughts?
Take the two values that you come up with and subtract them.
Okay, yeah, so if I take the area where Z is less than 0.4, that gives me a little more than I need. That gives me everything to the left of 4. But if I subtract off or chop off the initial part where I want to start my reading and chop off everything to the left of -1.17, then I've got exactly that. I've got this area between -1.17 and 0.4 because subtraction here chops off the area to the left of where I don't want to go any further. So that's how we translate betweens, is start with the upper bound, calculate its entire area, and subtract from it the area of the lower bound. Okay, so let's go consult our table. Let's see if 0.4 is going to be on my paste. Oh, would you look at that? Okay, I don't quite have the 0.4, so we're going to go back to the other table to read it. We already know that the probability Z less than or equal to -1.17 is 0.121, but let's go get this other probability. And what we're interested in is Z less than 0.4. So somebody help me out with that. Somebody that I haven't heard from yet, maybe see if you can find the area to the left of 0.4. Come on, guys.
Alina put the answer in the comments.
Oh, okay. Can you say it, Alina? You have a mic? Apparently not, or you probably would have done that. Okay, 0.6554. I'm not seeing it, but. Okay, so that's the area to the left of 0.4. And then we have to subtract from that our 0.121. Okay, so the area I've got shaded here corresponds to 0.5344 of the total area under the curve of that normal. So that, remember, this is converted to Z. All right, so we can finally answer that question. Question being, find the probability of randomly selected 3-year-old girl. So there's about sorry guys, this is kind of semi-behaving. Okay, so the probability of the randomly selected 3-year-old girl is between 35 and 40 inches tall. Okay, so we now have a tool. We have a way to take a normal random variable and calculate probabilities. So let's look at a new random variable and talk about this. I want to introduce a calculator function before we get started. Okay, the calculator, we're not going to use PDF for normal. Now, let me go back here. I'll tell you what I'm going to do. Let's use the calculator to get this same probability. So remember, we were looking at this in terms of X was the probability that 35 less than X less than 40. And we discovered that's equivalent to a normal probability of negative 1.17 less than Z less than 0.4. If we use the calculator, we would use normal CDF, and we're going to put the minimum value, the maximum value, mu, and sigma. So if we directly read from the underlying random variable x, to answer this same question, we can put our 35 here, our 40 here, and mu was 38.72. And sigma was, shoot, should have looked at that, 3.17. Okay, so if we did this right, we should get the same result. So nab your calculators, and you're going to go to the same place to your distribution. So I'm going to do second distribution, and it's nice and up front here. It's your second option. We're not really going to discuss or use normal PDF, so just pretty much ignore that. But normal CDF is going to give us the area between two values. So for my lower bound, I'm going to put 35. My upper bound was 40. That's all based on the question. The random variable itself had a mean of 38.72 and a sigma of 3.17. Okay, so it's all populated, and it comes in at 0.53651. Why is that different, do you suppose, than the answer we got using the table?
That's the exact answer rather than in the estimation.
Yeah, the table is finite, right? It's basically said, I'm going to increment, by these amounts and get you pretty darn close to your answer, but the calculator can be more specific and be more accurate. Okay, so we got 0.5365, and generally when we answer our probabilities, we answer with 4 decimal places. So 0.5365 rounded to the nearest 4 places. Okay, so that gives us some extra power here. We've got one way of doing it, and I want you to understand how to do it either way, whether you're asked to convert to a z-score and look it up on the table, or asked to translate it to the calculator function. Okay, so let's look at this question. What proportion of pregnancies last more than 270 days if the lengths are distributed normally with a mean of 266 and a standard deviation of 16? Okay, so we got an entirely different underlying random variable x. This is 266, 1 standard deviation on either side, so this would be 250, and then 76 and 6, and this would be 282. Or no, 282. Okay, so 1 standard deviation on either side. So for part A, we're asked for the probability or what proportion of pregnancies last more than 270 days. So that's x is greater than 270. So there's 266, so 270 is somewhere about right here-ish. But this is different. This is asking what proportion lasts more, so that's the area to the right of the curve. Well, we don't know that, but we can take 1, the total area, minus the probability left of the curve. And so we'll take the total area and chop off the other side of this to get a right-hand side. So we're just using a complement. So if I take 1 minus the probability that x is less than 270, I have my result here for part A. So let's convert x to z. Okay, then z is going to be equal to x value minus mu 266 divided by standard deviation of 16. And so we get okay, so what we really want for A is the probability. We want 1 minus the probability z less than 0.25. Okay, so back to our standard normal table. Less than 0.25. Remember, this is giving us less than. And then 0.25, I come over here. And 0.5987. Okay, so that's 0.4013. Let's do the same problem on the calculator. Okay, on the calculator, this is going to be normal CDF. And the smallest value I'm interested in is 270. Notice I can go back to my original random variable. I don't have to use the Z score. So for 270 is the minimum. And then it goes on forever. So in terms of the calculator, the biggest number the calculator knows is 1 times 10 to the 99. So we use a scientific notation, 1e99, that's 1 times 10 to the 99th power. And that is as close to infinity as our calculator gets. So that takes us from 270 to forever. And then we'll just plug in the original underlying mu and sigma. So 266 and 16. Let's plug it in. I like doing both because then it checks my work on the standard normal. Okay, our lower bound is 270. And the way you get to the EE is right here, so I'm just going to say oops. 1 second EE, it's above the comma, and then 99. 266, 16. Okay, 0.4013 if we round. Okay, this time we did get the exact same number, and it's just because we weren't far away from the numbers on the table that time. All right. Okay, so you've got a calculator method and you've got the standard normal table method. Use both. Let's look at a different problem here. The heights of pediatricians' 3-year-old females are approximately normally distributed with the mean 38.72 and the standard deviation 3.17. We're back to that random variable. Find the height of a 3-year-old female at the 20th percentile. Okay, so the 20th percentile is where okay, so that's where the area to the left of X is 0.20, 20% probability that randomly selected or 20% of the population fits into that. Okay, so what we're really after is the X. So what this is saying is that if Z equals X minus mu over sigma, that's how we calculated Z. Well, we can solve this for X and get the X from a Z. We've already got mu and sigma. So we need to find a Z where the area to the left is 0.20. Now that's a little trickier. We got to kind of fish through all of these areas and find the closest thing we can to 0.20. And it's down here somewhere. Okay, so somewhere between these two, the 0.2005 and the 0.1997. So that would be negative 0.8, and I'm going to say negative 0.845. Okay, so now we've got a Z value to plug into our formula. So X is going to be equal to mu, which is 38.72, plus my Z-score of negative 0.845 times sigma, which is 3.17. That comes out to about 36.1. Okay, so we found this is 36.1 in terms of X. Okay, and then this part over here gives you the calculator function. I'm going to save and post this very slideshow that I've marked up. I hope it looks okay. And I want you guys on your own to read this last slide. And essentially that means you need to be able to find Z sub alpha, understand what Z sub alpha means. I'll give you a quick overview. We're about out of time. So it's the Z-score where the area to the right is alpha. So if I wanted Z of 0.1 and the table itself gives us areas to the left. So we'll just take that subscript and complement it real quick, and then I can just go get the Z-score of its complement and verify what is going on here and why the Z sub 0.10 equals 1.28. And then there's an alternate here for the calculator that corresponds to the inverse norm. So if I say, give me the area, here's the mean and standard deviation, give me the Z, the X score that matches this, or if I had this converted to standard norm, will give me the Z-score. So this works and does what we just did here. So in this case, I could get my answer by saying INV norm. This is in the same location on your calculator. The area I'm interested in is 0.20. Now it's the area to the left, and the mean is 38.72, and the standard deviation is 3.17. Go find that on your calculator and verify that you get 36.1 as your result, because we did it using the formula and this does it using the calculator. Okay, so that's going to be a wrap. I'm going to put something online here